Okay, back to fairly basic ones. So the integral of the secant 3x dx. Okay, what's u going to be? 3x, good. And du would be 3dx. So we would rewrite this. Secant of u du. Now let's check. Secant, the u is 3x. The dx is there, so what do we need to do about this 3? We'll account for that by pulling out a 1/3. Now we're ready to find the antiderivative of that, which is one of the ones you were given today. It's natural log of the secant u plus tangent u. And then always remember plus a constant. We could take this one step further to replace our u with the 3x. Plus a constant. Okay, now go ahead and try your hand at number 9. Okay, so your u is x to the 4th minus 5. Du would be 4x to the 3rd dx. And then you can check your rest of your work. Okay. So in number 10, what do you think is going to be our u? Yeah, that's also raised to an exponent, so it's just going to be u is the natural log of x. So what is the derivative of that? 1 over x dx, which we're liking that because we have that 1 over x dx there, so that's good. Let's rewrite this and see what this looks like. So 1 over, this is going to be u squared, careful not to leave that off, du. So let's make sure everything's there. So 1, the u squared would be this, and then du is 1 over x, so 1 over x dx. It looks like everything's accounted for. So algebraically, what may help to rewrite this? U to the negative 2 du, and now when we find the antiderivative of that, you're just going to get negative 2 plus 1 is to the negative 1 over negative 1 plus a constant, which if we plugged in u, that can also be 1 over u. Okay, let's look at 11. Alright, first of all, I'm thinking I'm going to let my u be what? The square root of x, right? Which, if I rewrote that as an exponent, that would be x to the 1/2 power. That might help a little bit. So what would be the derivative of x to the 1/2 power? 1/2 x to the negative 1/2. Now, just to simplify that so that we can look at it in comparison to our original, how else could I rewrite this? 1 over 2, and if we bring that x to the negative 1/2 power down to the bottom, it would be this. Now let's come back over here. So this would be e to the u du. Now let's check everything. Let's be real careful. So e to the square root of x, that's e to the u. Du is the 1 over 2, so, and then the square root of x. So this 1 over the square root of x is here. Dx, almost forgot the dx. Okay, what's missing? This 2 here, so that's like a 1/2, so what do we need? A 2. Whoops. A 2, so that's just going to be, let's evaluate this now. So that's just going to be, bring our 2 down. That's just going to be e to the u plus a constant. And if we replace our u, it's going to be the square root of x plus a constant. So doing some algebra over here, some extra steps on the algebra may help you match this up. Okay, another example. Let's start with our u. So u is going to be what? Let's try the denominator because we're working with our natural log. So if you tried secant squared x first and then you see that it didn't work out, you can just come back and try the second term. So if I say let's let u be 1 over tangent x, then du, and the reason why I did that is because I know the derivative of a tangent is secant squared, so I was thinking ahead, you know. But if I didn't and I tried it, you would see that this is clearly the u that we're looking for. So the derivative of 1 is just a 0. What's the derivative of tangent x? Secant squared x dx, which I was hoping for. So now that's just a 1 over u du. And the nice thing on this one is that everything's accounted for. So we're just going to evaluate here and get the natural log of u plus a constant, or replacing u, we get 1 plus tangent x plus a constant. Okay, and then our next one is going to be e to the x divided by e to the x plus 1 dx. So write that one down and try it. Okay, so let's check our work on this. We let our u be the denominator. The derivative of that would be e to the x dx. Works out nicely. Everything's going to be accounted for, and we're just ready to calculate here. So that's going to be the natural log of the absolute value of u plus a constant. We plug that value back in, but in this particular case, because u is e to the x plus 1, that's always going to be greater than 0, then we don't necessarily need the absolute value bars there. Okay, so e to the x 1 plus tangent e to the x. So we need to determine what our u is going to be. What do you think? Well, if we did 1 plus tangent x, what would be the derivative of this? Secant squared, so we don't want all that in there. So first of all, we're going to back up and, like I said, if you're not sure, try it. And then when it's not making sense, just pick another, try again. So then u is that, and then we'll say, well, e to the x du is e to the x dx. Okay, so if we were to rewrite this, we would have 1 plus tangent of u du. Now let's see. 1 plus tangent u, so that takes care of all of this. Du is e to the x dx, so the du is e to the x dx. So this is what we have. Now, you can do it term for term. Remember, this could be broken apart, so that it could be term by term. So what would be the antiderivative of this? Just u plus, or actually, and what about for tangent u, the integral of tangent u from today's theorem is going to be natural log minus natural log of the cosine of u plus a constant. Okay, so if we plugged in for u, replaced u with e to the x, that would be e to the x minus the natural log of the cosine of e to the x plus a constant. We're just going to keep doing lots of examples, because the more examples you see, the little bit better you become at working with these.